In this video, I want to talk about the least squares method in matrix algebra. Matrices are basically representations of numbers, and the reason why we use matrices is to hold all of the observations of a given data set into just one single object. Let me give you an example. Suppose you're trying to predict the GPAs of students, and your y variable is GPA. Next, you have predictors such as, let's say, number of hours student studies, the major, and others. The model that you're trying to predict is basically one that contains the y variable, and you want to get an estimation of the y-intercept and then the slopes for every variable. Let's say x1, let's say x2, where x1, x2 represent just basically, let's say, the number of hours of study, major, and such, and so on. Now, how can we represent all of the values in a data set in just one single object? Well, I can get the y object to represent not just one single GPA, let's say 3.2 or let's say 3.8, but all of the GPAs together concatenated. So for example, the GPA of the first student can be this observation, and I can concatenate the rest of the GPAs in there. So this is called a matrix. Because it has just one single column, it has a special name, and it's called a vector. So, for example, once again, I can create y, but now my y won't be just one number, but a concatenation of objects. Let's say the GPAs of all of the students in a given data set. Now, the next thing is the predictors. Predictors can be many, like I mentioned some examples, but the way the matrices represent this in regression is that we can concatenate those in columns. So for example, this value would be the value of the predictor for the first observation, the first predictor. It might be, let's say, the number of hours that the student studies or so on. The second value here might represent the second variable. It might be, let's say, the measure of the student, and so on. So we have here basically a lot of predictors, and what we have in each predictor is basically the representation of them are concatenated into what we call a matrix. This is called in regression the model matrix, and it has a special name, or it's called the design matrix as well. So the only difference from the predictors that are concatenated into columns as opposed to the model matrix is that we have to put a column of ones first to represent the y-intercept. So having said that, now we have a representation that allows us to put all of the values of a data set together so we can estimate everything at the same time. The idea to do this is to get estimates of these parameters all at once so that I don't have to get formulas for each one of them. So as we saw in simple linear regression, we might have to compute a formula for beta 0, formula for beta 1, but instead we want to get just every single parameter estimated at once. So the design matrix is a very special matrix in regression because it contains all of the predictors. And like I mentioned, the special thing of this matrix is that the first column represents a y-intercept and is a column of all ones. So for example, in our case, if I have a design matrix to predict the GPA, the first column is the column of ones for all of the observations, but next I can have the first predictor, let's say the number of hours that the student studies, first observation, let's say the second observation up to the nth observation, and so on. the other column, the next one might be the major or some other columns like that. But all of these values are concatenated into what we call the design matrix. Now, there's a special condition that we have to have for the design matrix, and that is that the columns must be independent. They can't have what we call singularities. A singularity happens when two columns are multiples or combinations of other columns. Let me give you an example. Suppose you have a predictor, and that predictor is, let's say, degrees in Celsius. You can't have another predictor such as degrees in Fahrenheit because they are combinations of the columns. So they are not independent. They have some singularities. In other words, they can be, the columns are the same, it's just basically multiplied by another number or something like that. So that's the only condition. The second thing is that we want these columns to be as independent as possible. So where are we going with this? Well, the way that this works is that with matrix notation, all of the software that you can see, for example, R, SAS, Python, JOMP, or whatever software you might use to get a regression parameter estimates, you can get them all at once by using just this single formula, and that is the beta hat. And you have the X matrix, which is the design matrix, multiplied by itself using this notation that represents a transpose of a matrix that basically changes the rows to the columns, basically. So you multiplied X transpose X, get the inverse of that. And again, we don't have to remember that for any of the quizzes or exams in this course, but it's just that we have to basically see why we want to do this matrix notation, and then X transpose times Y. So what this formula does is that it gets all of the parameter estimates at once, and we will see an example. This formula allows us to get the minimum SSE. SSE is the sum of the errors squared. In other words, the sum of the residuals, the actual minus the predicted values squared. So what I'm trying to say with this is if you have an SSE value, then the estimates of beta 0 and beta 1 are going to be such that the minimum value of the SSE is obtained if you use that specific formula. So let me give you some other intuition. Another important notation is that now the predicted values, we can obtain them all at once by using the design matrix multiplied times the parameter estimate vector. So in other words, if we have the let's say the observations for the predictors for the first observation, and this might be number of hours of study. To predict the GPA, this might be something related to the major. So, and these are the parameter estimates. If I want to multiply these two matrices, then what happens in matrix multiplication is that the first row is multiplied times the column of the parameter estimate to get that specific first prediction, and so on. So it happens the same way with the second observation, the third, and so that I can get all the predictions at once. Another intuition for that is that just think about it this way. SSE is the sum of squared errors because it is a squared value. Like I mentioned, the sum of the residuals squared is a function that is a convex function. It looks like a parabola shaped. And let's say that you have just the y-intercept and the slope. So this is a 3D representation because you have in one axis beta 0 and another axis beta 1 and then SSE. If you plotted that, you would get this bowl-shaped function. So now the idea is, what gets the lowest SSE? What values of beta 0 and beta 1 get the lowest value for SSE? What happens, the mathematical intuition is that we get what we call the derivative of SSE with respect to these beta vectors, or these two beta values, beta 0 and beta 1. This is called the gradient. Just think of the gradient as if you were, let's say, driving over a road, and then it might be, a gradient that is going up, a gradient that is going down. So just think if you are here and you're trying to go to the lowest point, then your direction for the gradient might be just to go down. Okay? But there's a specific intuition that you can visualize here, is that because this is a bowl-shaped function, a convex function, the place where you get the lowest SSE is where this gradient is equal to 0. And that would be just the point where it might be just the lowest point, and you can see that this would be just exactly flat, 0. So if you get the derivative, which is the same as the gradient, and you set that to 0, if you solve that, if you set these values to 0 and then you start solving for beta, then you get this formula. And that's the reason why we use it, because in that place, that gradient is exactly 0. So you get the lowest SSE. Another visual intuition that I can show you is this. We can get many y-intercepts and many slopes. I mean, this is infinite values of y-intercepts and slopes. But we want to get the best one, the one that has the minimum SSE, or in other words, the minimum MSE, which is the same thing. So the way that it works is that the formula that you just saw, the x transpose x inverse x transpose y, basically gets the values of the y-intercept and the slope that gets the minimum SSE value. So in other words, it just arrives at that slope and that y-intercept that basically make these SSE or MSE, which is just the mean. In other words, SSE divided by the degrees of freedom, it gets that to be a minimum.